Our webinar. As you've probably just been notified, we will be recording the webinar today to let everybody know. Thank you for joining today. We're very excited to have you all with us and have a chance to showcase some really exciting work by one of our latest Center for Analytics initiatives by the Dr. Frank Rudzicz's lab, focused on actigraphy, but also voices in mental health, using an uh, adopting an AI-driven diagnosis approach through speech, language, and other data. So before we begin, I want to introduce myself. I'm Francis Jeanson. I'm the head of the Center for Analytics at the Ontario Brain Institute. And before we begin, I just wanted to have the opportunity to acknowledge this land, its nature, and its people, in particular the Anishinaabe, the Mississaugas of the Credit, the Wendat, the Haudenosaunee, and every other nations, recorded or unrecorded, who have taken care of this land long before us. And this is land which we must continue to take care of together. So I'll start with a bit of background on OBI and the Center for Analytics, and then we'll follow with the presentation by Rahimi from Frank Rudzicz's lab on the work that they've done through the Center for Analytics. So let me begin with a bit of background on OBI. So the Ontario Brain Institute is a not-for-profit organization that's really aimed at supporting research and innovation in brain health. We work with a number of institutions such as hospitals and universities across Ontario, but also Canada and even internationally on establishing highly collaborative research networks to focus on major brain disorder areas. We work also very closely with commercial innovators, from startups to SMEs and larger organizations that are developing technologies and helping disseminate these technologies and approaches to better diagnose, predict, and even treat patients. And ultimately, it's about connecting this research and this innovation with the patients through a connected care network, where we have a lot of engagement with patient communities, as well as the caregivers and their circle of care. On the informatics side, OBI has put a lot of effort in supporting this research happening across major brain disorder areas. Here you see a large network with the sort of circles near the center, including CAMBIND, which is a large integrated discovery program focused on major depressive disorder. We also have a large network through POND, focused on neurodevelopmental disorders. Another network with CPNet, focused on cerebral palsy. The CALM network, focused on multiple mental health disorders in children and youth. And finally, the Transcendent network, focused on concussion across the ages from children, adolescents, and adults. All these major programs have research expertise across these different institutions that they're connected to, which you see in this network here, that really span across the province of Ontario, Canada, and beyond. What we really put a lot of emphasis on is collecting rich and standardized data on a centralized platform that we call BrainCode. And this is the diagram that you see here in the middle. It's really a secure platform to collect rich research data that enables these researchers to collaborate and make new discoveries about brain health. The platform also enables secondary use of these data in an open science approach, enabling researchers even outside to come and look at what data are available and that could help them answer their research questions. So as it's shown here on the right, we have over 40 institutions that are part of this network, well over 1,000 users on the BrainCode platform. We standardize data. We work a lot on data federation and enabling this harmonization. We also support data linking, which enables the augmentation of data through linking with other databases and ultimately facilitating data analysis. So this has created a really rich neuroscience discovery opportunity. We have multimodal data collected across these networks that span from the wearables and sensor type data, which we'll actually talk a little bit about today, molecular data that are often collected through this research, genomics data, neuroimaging data, and clinical data. And this spans across these major brain disorder areas, which really supports the opportunity to better understand the complexity of brain disorders through a multimodal approach. Here's a quick snapshot of the BrainCode platform and the data that are available on the platform that enables these researchers to collaborate. You can visit the platform on the BrainCode website at braincode.ca, and you'll see sort of the richness of these data across clinical imaging, molecular genomics, and beyond. We have strong standards. We work on common data elements so that essentially what we call uh, uh, common measures are collected the same way, and the same measures are collected across these brain disorder areas through these research studies. And ultimately, we also enable this advanced linking of data using encrypted homomorphic approaches, which preserves participant privacy. So this data taken together has really compiled into a terrific set of data releases on the BrainCode platform, including for PON so far, CPNet, EPLink, Cambine, Connect, and Andri. And you'll see the various modalities that are available based on the specialization that these networks focus on, with a growing number of data sets every year. What we've noticed, though, in the last few years at the Ontario Brain Institute is that we do have some challenges related to making use of these multimodal data. We don't always have the right skill sets to look at the combination of these modalities. We don't always have the technology and the computing required to also make the predictions or the modeling that we want to model, especially leveraging modern techniques like machine learning and artificial intelligence. And we also need to support the strategy for how do we bring these new technologies to the bedside? How do we make these technologies available for patients and even for their community of care? These are big challenges that we've aimed to solve and support finding solutions for through the Center for Analytics. And so this is really the core mission for the Center for Analytics, is to support the development of skill sets in this multimodal neuroscience space. We also do a lot of work around supporting the access to high quality data through data that are available on BrainCode, access to modern computing on the cloud, and also building an ecosystem of methods and tools that can be leveraged by the community to further advance their technology and ultimately their ability to better understand, predict, and treat brain disorders. And ultimately, we want to support them also with their translational strategy. How do you convert your technology to a solution that can be made available to patients, to clinicians, and to the circle of care? So we provide ways to help validate these technology through access to more data or analytical support. We can also help support the pathway to navigate regulatory and privacy compliance, and other opportunities to build up their capacity through making their applications available in a productized way, in a way that is essentially ready for prime time. And so our focus through the Center for Analytics has been to support what we call analytics initiatives, of which Dr. Frank Rudzicz's lab is one of them. And over the year, we've actually had a number of webinars showcasing the work from each of these initiatives that are really aiming at developing the capacity in these three core areas: the skills development, accelerating technology, and translation. So you can see here on the slide a number of webinars that we've had so far. And today we're going to be focusing on the work by Frank Rudzic and Ellie, who will be presenting in a moment on the techniques that they've developed to better understand mental health. And last but not least, we'll have another webinar coming up in a few weeks with Dr. Roger Zemek's lab from the University of Ottawa, looking at autonomic dysfunction using vital sign indicators. So stay tuned for this. We also have a new cohort that will be announced shortly of new CFA projects that are just about to start. So I'm going to end with this last slide with a few resources which the group here might benefit from. We have a number of methods tutorials that are developed by these analytics initiatives that are available on GitHub. And if you look at this link on the left, or the QR code, you'll be able to access these. We also have these webinars that are recorded that we make available on YouTube, on our YouTube channel for the Center for Analytics, which you can access on the right. And I want to reemphasize the next upcoming webinar with Dr. Roger Zemek's lab that you'll be able to access if you go and visit the Brain Institute's website, if you go to the news and events section. So that's it for the bit of background on OBI and the Center for Analytics. I want to now introduce our speaker. Ilahi Rahimi is a PhD student in computer science at Dalhousie University under the supervision of Dr. Frank Rudzicz. Her research focuses on machine learning and language models, examining how they reason, how reliably they perform, and how they can be leveraged to advance mental health research. So thank you very much, Ali, for joining us today, and Frank as well. I'll pass it on to you.
Thank you so much, Francis, for the introduction. And I guess I should be start. I can share my slides right now, but so okay, so I think sorry, it's been a little bit like I cannot see my screen. I don't know why.
Oh,
We were just checking it right now, but
you see the PowerPoints?
no,
Yeah.
I don't know what happened. Okay, can you see my screen?
Yes. We just don't see the full screen yet, but
Mm,
there we go. Yeah,
okay.
that should work. Yeah, it's full screen.
Okay, great. Okay, so today I'm going to be presenting on work on contrastive learning and actigraphy data to predict relapse, depression relapse. And this work has been done with support from Ontario Brain Institute and Brain Code Data Platform, and also all the data is coming from CanBind. So what is the incentive behind this work? So the thing is, depression relapse happens almost in 50% of the people who are in remission state within 5 years. Meaning that if a person is depressed and now it's in remission state and they are doing okay, within 5 years, they are probably gonna experience relapse again. So it's really an important subject, and we would like to monitor these patients before they go through a full episode of depression. One of the practice or method that clinicians usually do is that they track these patients within 8 weeks or 6 weeks apart from each other. And they use a rating scale called MADRS, and based on that score, they decide if the patient is doing okay or they are experiencing some symptoms that needs to be addressed. One of the problems with this way of monitoring patient is that, let's say you see a clinician today and the next visit is going to be in 8 weeks. So in week 2, you might experience some episodes, but since you're not going to see the clinician, by the time you are going to see them, you are already in a really poor state. So it's really important to monitor these patients constantly, and when their behavior or their symptoms are deviating from their stable state, we can, kind of notify the clinicians and maybe intervene. Another problem that I found in this data set is that 70% of this MADRS score has nothing to do with the depression relapse, meaning that the patient was in a really good mood the time that they visit the clinician, but the next visit, all of a sudden they were depressed. So it's not like there is always like 100% correlation between MADRS score and the relapse. So that's another thing that we cannot just through, giving those questions and asking those symptoms and giving them a score, be like, okay, this person is doing good or this person is not doing good. So that's really important to monitor their symptoms continuously and make sure they are under a stable state. Okay, what is the cohort of this data set? We have 89 patients that have been collected from 5 different sites, and they have been monitored for over 2 years. And we are using actigraphy data, which means that they are just wearing a watch. It's completely passive. And this watch is minute by minute capturing some signals related to their sleep, their activity, their circadian rhythms, and everything. And we call a person a relapser when for 2 consecutive visits, their MADRS score is more than 22. And also they are experiencing some, suicidal thoughts or behaviors. So, okay, out of these like millions of data points that we have, we need to come up with a criteria, with a set of features that we can do meaningful analysis on them. Because as I said, we are capturing the signals minute by minute. So it's millions of data points. So we came up with 4 criteria to select those features. One is a predictive power, meaning if we select this feature, is it going to be able to separate relapser from non-relapsers? If yes, we're going to keep that feature. And we're going to use area under curve. And if it's more than 50%, we're going to consider that feature as an important feature. The other one is temporal signal, meaning that as we are getting close to the relapse, is this feature is changing or it's just constant? If it's not changing, then that's not gonna, differentiate relapsers from non-relapsers. The other one is low redundancy. If 2 features have a high correlation with each other, there is no need of using both of them. So we just keep one. And the last one is simplicity. Actually, this is kind of the most important one as well, because we want to come up with features that is easy to explain and also interpret. Otherwise, if I tell you, let's say there are, 100 features that has some sort of correlation with relapse, but I cannot do anything about it because it's hard to interpret, it's going to be of no use. So based on those criteria, we selected 6 features. Intra-daily variability, meaning that how fragmented their activity is within a day. The total sleep time, sleep efficiency, mean of their activity, sleep onset latency from the time they wake up to the time they go to sleep, um, measuring their activity, and also how many times they get up during the sleep. So now we have a set of features, but these features, we need to track them over time. One thing we're going to do is that for each visit, let's say the day of the visit is day 0. We're going to look backward 1 week, 2 weeks, and 4 weeks and aggregate those features over those windows. For example, if you have 1 or 2 nights of bad sleep, it might be shown in the 1 week window, but that's not going to be, seen in a 1 month of your sleep, pattern. Or there are some gradual patterns that might happen within a month, but you're not gonna see it in 1 week. So that's really important to have different time window and aggregate those features over the window to see the trend of those features. So, and for each feature, those 6 features, we're gonna consider mean, what is the stable or the average of those features, the standard deviation, how much they are going to fluctuate, and the velocity, in which direction they are changing. So all in all, we have 6 features, 3 um, um, statistical feature, and also 3 time window. So it makes us 54 features. Besides that, we're going to add another 18 feature, and that one is availability feature. What do I mean by that? Let's say in the first window, you have 40% data available. And let's talk about the sleep feature. So yes, one night you slept for 10 hours, the other night it was 8 and the other night it was 3 hours, but you don't have the hours for other nights. So it fluctuates a lot because you have a little bit of data. You cannot track it over time. But if you have the full window, then those features or those numbers are more reliable. So that's something that I want my model to learn. When you have more data, rely on those more compared to the time that your time window is you have low availability. So all in all, we have 72 features. Okay, this was the pre-processing part. And now I want to look at the label part and label my data set. So when the relapse happens, I'm going to look at different time window as well. If it's more than 84 days, meaning 12 weeks, I'm going to consider that zone or that period as a stable or positive period. As I'm getting close to the relapse, then I'm going to consider those as negative. From 2 weeks to 12 weeks, 4 weeks to 12 weeks, it's early prodrome. And the late prodrome is going to be 2 weeks to 4 weeks. And then the imminent one is going to be 0 to 14, just 2 weeks before the relapse happens. I'm going to consider those as negative samples. So now I have the pre-processing part. I selected the features. I have these labels as well. Now I need to decide what kind of model I would like to use to train this data. Okay, so the obvious or the common option is to go with the supervised sequence models like LSTMs or transformers. But in our particular data set, we have 427 stable zone or visits and only 21 prodrome, meaning it's super imbalanced. And LSTM or transformers for that matter, they are really data hungry. And if you just use LSTM out of the shelf, it's going to be overfitted. And even when it tells you it's not going to experience relapse, even if it says that all the samples are not going to experience relapse, you are still going to get a high accuracy because most of the samples are non-relapsers. So obviously that's not the kind of model we want to use. That's why we decided to go with contrastive learning. Contrastive embedding models, they are not anything fancy. The only thing that is a little bit fancy about them is the loss function. So these models are like any other model, but you train it with a different loss function. For our particular case, we use just a simple MLP model, like 72 features comes in to 256 layers of neurons, and then at the end, 64 as the embedding feature. But the loss is unique. The way we train the loss is like this. So let's say a person A is in a stable condition. We're going to consider another stable visit of the same patient, patient A, as similar, and we try to define the loss in a way that it pulls these two stable period together. And the negative ones, if you remember, it was about the prodromal period. So for those, we're going to be like, okay, if it's the prodrome period of patient B or patient A, I'm going to consider both. With this difference that for the same patient, I'm going to penalize it harder. I'm going to consider rate twice as another patient. Why? Because for patient A who experienced relapse, everything is similar, right? It's the same watch, it's the same daily activity, everything is the same. It's the same demographics and everything. But this person experienced relapse, meaning there must be some um, clinical actually features that happen that this person is experiencing relapse. That's why I'm going to consider those data. I'm going to penalize those data twice as the other patient relapse to make sure we understand what makes a person who was okay for a time period going through a relapse after a certain point. So by doing so, we are creating a manifold. So this manifold is like a certain area of the space, 64 dimension, that these stable people exist in that area. And the people who experience relapse are going to be as far as possible from them. So when a new visit comes now, I'm gonna be doing, I'm gonna fit a KNN model to this stable period, to this stable manifold, sorry, and I'm gonna look at the average distance of, because we had 400 visits almost roughly, so that's why I selected the square root of that, 20. I'm gonna compare this new visit to 20 points in this manifold and be like how far on average you are from the stable manifold. So we're gonna define it actually like that. We're gonna define a risk score that when a new visit comes, I'm gonna measure the distance of that new visit to 20 nearest neighbor and then average it over the baseline that is going to be all these points in the manifold. I'm going to consider what is the average distance of these points in the manifold. That's going to be my baseline. And when a new comes, I'm going to just consider 20 of them and average over them. And the risk score tells me that if this data is close to the centroid or not. And if it's close, I'm going to get 1. It's okay. But as I get further, then it's become concerning, meaning that this patient is deviating from their healthy, stable trajectory. So all in all, this is end-to-end relapse prediction architecture. We have raw input. We're going to do feature analysis and extract 6 features. We're going to aggregate them over different time windows. We're going to feed them to a contrastive encoder to have a manifold of those stable patients or visits. And when a new visits come, I'm going to, measure the distance between the manifold and that visit. And based on the distance, I'm going to decide if it's a word concerning window for that person or visit for that person or not. So you can see from here, for example, this patient was, the MADRS score was increasing over time. And as you can see, our risk score is also capable of following almost the same trajectory and going over a threshold, a dynamic threshold, and telling us, okay, this person might experience relapse in the future. On this side, you can see the manifold of stable people. Yes, there are some relapsers still exist in this manifold as well. It's not 100% good, but you can see they are scattered all over the place. But these blue dots, which are the stable people, they are, pretty much close to each other. And we also compare our results with another publication from Kanbine team, and we can see the true positive for them was 14, for us was 34. We are still far from the ideal, but we can see the method works, and the main problem for this data set is the scarcity of the relapsers. And the true negative is for them was 97, for us was 84, and false positive rate was relatively lower, and false alarm rate was also a lot lower, meaning that it's not gonna create fatigue for clinicians and alarming them constantly when a patient is not going through a relapse. So yeah, that was basically it.
That's fantastic. Thank you, Ellie.
Yeah, my pleasure.
We got plenty of time for many questions, I'm hoping. I certainly have a few myself, but I wanted to first see if anybody from the audience had some questions for Ellie. And feel free to raise your hand or even ask your questions in the chat. Both options are fine. I'm not seeing any questions yet. Oh, Frank?
Um, Thanks for the presentation. This is exciting early work. I was wondering if you could talk a little bit about like if this was going to be something that we wanted to deploy or that others wanted to deploy in practice, and the class imbalance problem that you highlighted
Yeah.
was in existence. Like, are there any other approaches that you might have taken or that you would recommend others to take
Yeah.
to overcome that?
Yeah. So in terms of putting it into practice, I would say it's not doable yet because but I would say the method works. The only problem is that the data is so sparse and we don't have enough relapsers to make sure our methodology is reliable. But I would say this is really promising. And regarding the other like imbalanced data set, we can do obviously the easiest one that comes to mind is that to oversample the data that you don't have or downsample the ones that you have a lot from. So these are like this is not gonna work in this situation. Why? Because you're gonna consider data IID. Oversampling or undersampling is when the time doesn't matter. But in this case, time matters. So you cannot just oversample randomly or undersample randomly. And also you can, for example, another way is that to penalize, design the loss function to penalize the negative one, the positive one more. But that one is also not going to work because in best case scenario, it's just going to create, like make a distance between each individual, but it's not going to create a cluster. And when a new visit come, you still don't know what to do with that one. So those approaches probably are not going to work on this particular data set.
I think that's good to know for anyone thinking of deploying anything of this type.
Yeah, that's similar question related to so this is also actigraphy data, so it's wearable based data.
Yes.
Um, what was your sense of what's the required like minimum quality for this data and like how like were there conditions where you need like the participants or the patients had to wear the wearable for a period of time, or at what point did you have to essentially cut them out of the data analysis because there's not enough data points?
Yeah. So, like I would say you need at least 40%, the least you need per day, for your analysis to be reliable. But unfortunately, in this particular data set, we had months of not having anything because the patient was not wearing the watches or like sometimes weeks, especially before relapse, because that's the point that they just give up on everything. I try to use that one as a feature as well to see if a patient is not wearing, but unfortunately, there is so much correlation between even the positive ones. Some of the people who never experienced relapse, sometimes they are not wearing these watches. So it's not like an indication of separating relapsers from non-relapsers. But I would say we need more data in terms of people who experience relapse, and also we need like a consistent period of time that they are wearing the data and we can track their symptoms over time. It's just too abrupt right now. Sometimes for the patient, you have like, let's say in June, they have been visited and you get the MADRS score is 10, which means that they are doing okay. And then the next visit is probably in December because they didn't come to the clinicians. And so there is a lot of, missing data here. Yeah, I would say for this data to work, we need more relapsers and we need more data per day or per certain period of time, let's say weeks or months.
And what would you say that more is? Is it 10 times more or is it a couple like 2 or 3 times more?
I would say maybe even more than 10 times more. Yeah. Yeah.
To build something that's really robust and
Yes.
to generalize as well,
Yes.
right? Yeah,
Yes.
that's right. Do
And we
you,
can also be confident about our analysis. When I have only, let's say, 5 patients in total that experience relapse, no matter what is my, methodology, even if I get 100% accuracy, it's not going to be that reliable because it was only 5 patients and you can easily overfit to those patients.
Mhm.
So,
That's great. I have a few follow-ups, but I'll pause to see if anybody else would like to ask some questions.
I think, so.
No, I don't see any yet. And Ali, related uh, to the modeling, I noticed you were using KNN, I think, as a
Yes.
character neighbors approach for like the clustering, like to see where they fit against the centroid. Have you tried? Was there a reason why you selected that method in particular? Are there other methods?
Yeah, there are like you can use, let's say, a simple Euclidean distance, but that's not gonna be like where you wanna put the threshold to say, okay, if it's more than that or if it's less than that, I'm gonna consider it as a high risk or low risk. What matters here is that so, for example, this manifold might have different shapes. Sometimes it's like, yes, it's a cloud, but it's all scattered, all over the place. So the distances are big versus sometimes it's really, compact. So you need more data points. You need to get, a sense of how close these data are to each other, and then divided by a baseline to know, okay, if I say like on average data are within 0.5 and all of a sudden I get 1.5, then I have a sense of that. But if you just use, a simple distance, then you don't have that kind of understanding. So,
Very interesting. That
yeah.
makes sense. And I was looking at the risk score. The healthy concern and a clear concern. I remember that slide. I think it's on slide 12. Was it? I think so. That that makes me think of sort of standards of deviation, so to speak, right? When you're looking for a signal, as that's essentially the proximity to the centroid. Is that correct?
Yeah, but I wouldn't, it's just like for the sake of, an example, but it's not just the centroid. We consider 20 samples and just average over those, not
Right.
just the centroid.
Sorry, I think it's the previous slide, the one just before. Yeah,
Yeah, yeah,
the one below, slide 12.
okay.
This one here. Yeah, this is where you have like kind of these cutoff points, right? That you
Yes. Yes, this is something that I would say it's up to clinicians. I just went with my, understanding of the data, but I
right.
would say if I consider twice as concerning, I don't know if a clinician would consider it concerning. But based on because we had already ground truth, kinda, I would say two times more is concerning based on
Mhm.
the ground truth that we have. But a clinician might have a different opinion.
Right. Yeah, very helpful. It provides a framework, right, from which you can then
Yes,
build and then collect more data. And yeah,
exactly.
I don't see any other questions yet. Ellie, I do know that you've also done some preliminary work on the voice data,
Yes.
and that was another component of the project. I don't know if you wanted to say anything about that as well.
Yeah, I can just share my slides. Mm, okay. Okay, so this wellness data set, they have two modalities. One of them is speech, one was the actigraphy that we just discussed. So we have roughly 9,000 raw recordings. And so we need to somehow filter those, find the ones that actually can contribute to relapse prediction, extract some features based on that, and use it for our analysis. Based on the analysis that I've done, out of these almost 9,000 voice recordings, sorry, 58% of them are valid, and the rest are not useful for our analysis, especially for relapse prediction. So these audio files are like that. One of them is a patient is supposed to say a vowel for 5 seconds, And the other one is a free speech. Sometimes they are asked to, for example, describe their day or describe a happy event and those kind of tasks. So some samples are just based on vowels, and some others are, the patient is actually talking about an event. So we need two different strategies to see which one of those samples are valid. For the sustained vowel, we did this analysis. If it's more than 500, the RMS is more than 500, we're going to consider it as a file that probably the patient was speaking or, talking in that file. And the duration must be more than 5 seconds, which I think it was automatic, so all the files were actually 5 seconds. And we also consider a clipping limit, and if it's less than 5%, we're gonna keep it. For the free speech, we use SAD, and the SAD must detect the speech. And also the duration must be more than 30 seconds. The quality, the signal to noise ratio must be more than 10 dB. And for this kind of analysis, less than 10% is acceptable. And we have to make sure there is no other speaker in the audio. After doing all of this analysis, we realized that 20% of this file have low SNR. 26% of them have more than 5% distortion. 30% of them don't have any speech in it, and 6%, almost 7% of them have, there are multiple speaker being detected in those audios. So out of these different tasks and different speech samples we have, I would say sustained vowel is the least reliable one. We cannot use it that much because only 29% of those are valid. But the rest are relatively in a good position, and 60%, 70% of them are valid and can be used for analysis. So we can do two things. One is like just relying on acoustic feature extraction, especially for those tasks that the patient is talking about an event. We can extract features from those audios like jitter, loudness, and those kind of features. And if we want to do that, 932 patient date. Meaning that sometimes, for example, you as one patient, you might have, let's say, 100 recordings. So all in all, 932 patient dates are available for analysis, acoustic analysis. We also can transcribe them, which I did using Whisper. I transcribed almost 3,000 audio files. So we can do basic NLP tasks on those transcriptions. So for that, I was looking into some articles, and there are some basic NLP psychological kind of markers that we can use to predict if a person is going through a relapse or is already depressed or not. For example, one of them is like how many times they are using pronouns, their emotions, is it negative or positive, or they are using negative verbs or not. So we came up with 8 kind of psychological markers to assess those transcriptions. And the only thing that we found that has a positive correlation, and we can rely on it because the rest of those features either were not contributing that much or even had negative effects. But the only thing that had positive effects on finding if a person is experiencing a relapse or not was the negation ratio. As the patient is getting closer to a relapse, they are using more negative verbs and wouldn't, couldn't, shouldn't, and those kind of things. And so that can be one of the features for relapse or any sort of depression detection measurement. That was this task was mainly like cleaning the data, finding what we have, what we can do for the analysis, and doing just some simple analysis and see if we can find any sort of meaningful way of predicting relapse. And the only thing that I found was just this negation ratio. Yeah.
Fantastic. Thanks, Ellie.
Yeah, so and now I would say if anyone wants to work on these speech samples, I would say they are in a clean and, pre-processed condition, and they can just be used for any sort of model.
Yeah, it's a huge contribution onto itself. Just preparing the data, understanding it, filtering it out, and finding features. It's terrific.
Yeah, thank you.
That makes a lot of sense in terms, I mean, intuitively, it makes, I guess you could think the identifying, negation ratio having an impact.
Yeah.
Interesting how, yeah, I wonder if there are other features that are maybe you discover, I suppose, if you had more samples that are in better shape that you could actually use, but I guess that's to be determined. I see Stephanie has a hand up. Stephanie?
Yes, hello. First of all, I have to apologize. I'm walking between campuses, so there might be a bit of background noise here. Uh, Amazing work, Ellie.
Thank you.
Super excited to see the cleanup process of the speech sample happening. Just one clarification. So,
Yes.
did you say you only had 5 relapses in the actigraphy analysis?
No, we had
Oh,
28
no.
relapsers, uh,
Okay.
but among them, I would say 18 were kind of like had enough valid data points to be analyzed because most of them had single visit. Like they came during the remission state, and then the next time was the time that they were already, relapsed. So there was no trajectory to, analyze.
Okay. Yeah, because I was like the 28 makes way more sense. But so the restricting factor was the quality of the actigraphy data
Yes.
rather than um, not there not being sufficient relapse. Okay, and I guess you would encounter a similar problem looking at the voice data as well, right?
Oh, yes. Yes.
Yeah, yeah.
Yeah.
Okay, good, cool. Thank you. But amazing work. Looking forward
Yeah.
to
Thank you
seeing
so
more about
much.
it. Cheers.
Thank you so much.
Yeah, that's fantastic. Any other questions for Ellie? I don't see any others at the moment. Just to remind everybody, we are working with each project, including Ali's project here and Frank's, on methods tutorials, which aim to help share sort of the lessons learned in terms of data preparation, methods and techniques used. So we're hoping that, I think some of these methods and techniques could be shared with a the broader audience, the broader community for this work. And I think this particular data set is part of the Combine integrated discovery program. And I think Ellie, these data and work will be available through the Combine program initially. And then I think what we'll do with the Ontario Brain Institute is follow up with Combine and explore how maybe some of these data or process data could also be made available for other researchers and collaborators. So this is really exciting. And like you said, it's a tremendous amount of work that could then help kind of build a bit of what we call a pipeline, right? Where now any new data can come through the same pipeline, follow the same steps of pre-processing and prepare it for this type of analysis. So yeah, it's terrific. Great. I don't know if there's any other comment from Ali or Frank in closing.
I'll just like echo what was said earlier about Ellie's work. I think it's been really great, and I'm very happy with the progress so far.
Yeah.
Thank you.
Yeah, thank you. Okay, well, with that being said, I think we'll probably bring it to a close today, a few minutes before the end of the hour. So I want to thank again Dr. Frank Rudzik and Ellie for the terrific presentation and really the exciting work. It's been a fantastic year, and we're coming to the end of this year and projects. But like I mentioned, the methods tutorials will be made available on our GitHub, and this webinar recording will also be available on our YouTube channel. So stay tuned for that. And I mentioned it earlier, we have an upcoming webinar with Dr. Roger Zemek on March the 20th in a couple weeks' time. I think, and we have the link posted in the chat. Yes, yes. Thank you, Russia from the OBI team. Don't forget to register for that webinar as well. So thanks again, everybody. Have a wonderful day, and we'll see you all soon.
You as well. Bye-bye.
Thank you. Bye-bye.